Thank you very much, Christian. Thank you very, very much for the organizers to have me here to be able to speak. I will talk today about a definition, more or less. I called the talk "The City as a Prototypology," and that is important in the regard that a prototypology, as I call it, in contrast to a prototype, represents a seed for a configuration in a permanent state of evolution. Prototypologies are open to change and adaptation. In this light, I see cities as an open and flexible system that react to their local and immediate setting, even so they operate on a global scale. In that sense, and we talked about a lot in the last couple of days about models, I think personally that a prototypology, and I want to introduce this term as a discussion, is not a model, but a transient phase of an evolutionary space, and therefore always ahead of its type. So what I want to promote is that we as planners and architects have to think to design not models. Models are usually closed-up systems, but we have to start to design open processes which are ahead of what we conceive as the present, which brings us back to the idea of a future city. But usually, when we look around constructions worldwide, what we do are usually imported and closed up prototypes and images that reflects in the eyes of decision makers a global and universal modern. And therefore, and I think that is a misconception and misunderstanding, usually a successful path in the future. But with this import of images and visions, building materials like, for example, concrete and glass and steel are also associated with this term of modern, and in that sense become a universal representation of what I would like to call a copy and paste urbanism. What that leads to, I can give you a small example from the realm that I worked for in the last couple of years, is that African cities today, when they talk about development or when African cities talk about being modernized, usually these images are imported from different places around the world into a local setting, which usually makes no sense. Buildings like this one, right now, mushrooming all around Eastern Africa. Eastern Africa, for architects, I would describe as a paradise to plan in. So, for example, countries like Tanzania, countries like Kenya, countries like Sudan, usually have temperatures or climate conditions which, also in the case here in the highland of Ethiopia, do not go beyond 30 degrees Celsius maximum, and usually are also not dropping down lower than 10 degrees Celsius in the nights or in the rainy seasons. Therefore, what we heard yesterday from Hans-Jörg Leibundgut is actually that in those places we would not need to equip these buildings with technology. Cross-ventilation, open airflow would be just fine. But now what happens if we import these images from Dubai and Shanghai into an urban context of Ethiopia? Sun radiation in the highlands of Ethiopia being close as what we have realized yesterday at the height of the mountain, around 3,000 meters, make that these glass facade buildings are heating up behind their facades like pizza ovens. And what is the response of us architects and engineers? We put in even more technology. All of a sudden, an absurdness is happening that in the countries or in areas in the Eastern African context which would not need to put in technology as air conditioners, the only chance we have to cool down these buildings, because they are planned in such a bad way that you cannot open any window, is to put in an air conditioning. I lived for 3 years in Africa, and I can tell you more than 1/3 in the mornings where I woke up, I had no power. And you know why? Because of that. Because of bad planning of architects. Because of an absurd idea that only the global is conceived to be modern, while the local is to be seen as something locked up and something from the past. So what we're trying to do, or what we tried, and hopefully continue to try with the colleagues from Ethiopia in the school, is to understand or to kind of promote ideas of how a reverse modernism can happen. I would like to call this reverse modernism that we take ideas and experiences that we find in the so-called South, the so-called undeveloped areas, into our research, for example at the FCL in Singapore and the ETH in Zürich, understand the mechanisms and more or less promote ideas, technologies which are locally based and are, in the sense, a prototypology that means open for further development. So instead of bringing closed-up prototypes, models, and model towns to the south, I would like to show you in a very, very small example that we're doing right now, how maybe we can start to learn from the south, develop something in the north, and apply it also in the context of the so-called north. With this idea of these houses and with the construction of those houses, of course also the question comes in of how to construct these. So when you look right now at most of the models again being implemented, you find that construction methodologies are put in place, which are mostly based on models again coming from our areas. Reinforced concrete beam structures, hollow block structures, kind of erasing any kind of locality and any kind of local identity from the construction sites. That has a result. When we look at the consumption of construction materials, or the basic materials consumption in the world, you see that from 1950 to approximately today, the use of cement, aluminum, steel is constantly growing. And that is not the case, and we discussed that before, because we're consuming it mostly right now in Europe and North America. The reason for that is that mostly emerging and developing countries are seeking for those materials. But they're not seeking these materials because it is an indigenous materials for them to build with. They're seeking these materials because they follow role models. Here you see the chart for the world cement demand, and you see we're closely to 90% of the world cement demand comes from these emerging and developing territories. Or looking at steel, you see the same development, that close to 70% of the steel demand worldwide is asked in these developing territories. But when you look where, for example, the steel is produced worldwide, you find that in Africa, and I want to focus a little bit on Africa, that only 2 countries, mainly South Africa and Egypt, are actually producing steel. That means all other countries, and we saw so many maps in the last 2.5 days of showing where the urban population is going to be, where we have to construct on these buildings. It is a mismatch. We have a mismatch of production and consumption. And that, I think, cannot be very sustainable. When we look, for example, at this world steel production, China has almost half of the market, while Africa, you see, it is only at 2.8%. So, what will happen if countries in Africa follow the same path, follow the role model, follow the prototype of China? That would mean that a continent like Africa, and we know that from different media sources that we prognosticate that Africa would develop more or less like the Asian countries in the last 20 years, that this would result that today when we look at the CO2 emission worldwide, this is a map showing CO2 emission per country in 2012, that would lead us, looking at the African continent today, producing approximately 17 million tons of CO2, compared to China with 311 million tons of CO2. That if we kind of play the game out, and if we assume that Africa is following the same path as China, that we come up with an amount, I think I missed one, of 367 million tons of CO2 prognosticated in the year 2050. That is tomorrow. So the question is, can we as architects and planners, and these numbers, I mean, they're widely spread, that is not kind of a miracle to do these calculations, can we start to understand and can we develop ideas of how a local and so far unmodern material can be researched in such a way that we can apply it in the future in these areas where it is demanded? And this chart shows again the same idea, that if we continue, for example, with the steel production, that we reach almost 400 million tons of CO2, there could be maybe alternative path where we start to think about construction steel, or to substitute construction steel with something else that either kind of bends down the curve, or in a very, very optimistic approach, how we can actually understand material and building material to decrease the CO2 emission in developing territories. This optimistic approach would then lead maybe to not even kind of increasing the amount of CO2 emission, but decrease the amount of CO2 emission worldwide. And I said that cities should be understood globally, should be understood locally, but have, of course, a global impact. We are based in Singapore with our laboratory, and as I said many times before, and it's funny that I think this map you saw already in kind of different variations, the density map right now of population. You see that with that density map, you can also almost one-to-one overlay a map of the so-called developing territories or countries today. Most of them are found in Africa, some in South America, a lot, or some of them again in the area where we are located around the Southeast Asia territory. And with that, almost one-to-one is also the highest population growth happening worldwide. And with that, almost one-to-one along the equator belt, we talk about the tropical zone. But the tropical zone has a great advantage, that it is growing a material, or a building material I would call it, which so far was not on our agenda as a processed material, which is bamboo. You see here the natural habitat of bamboo, mostly concentrated again in Africa, South America, and the Southeast Asia region. And bamboo has one incredible property which we are, as architects and planners and constructors right now, very much interested. that is this capacity of tensile strength. Bamboo is a very strong material. And as seen in the BBC lately, an article saying booming bamboo, the next super material, we are trying to understand these characteristics and the properties of such a renewable and growing or organic material and making it available for the construction industry. Bamboo is a grass. That is actually the secret behind its fast growing. We heard from Stephen this morning that after a cycle already of 5 years, you can harvest bamboo and make it available as a building material. So you see here the chart. So compared to other timber we usually use in the construction area like oak or teak, beech, eucalyptus, bamboo has an incredible fast life cycle. And you don't have to replant bamboo. As it is a grass, and you know it from mowing your lawn, maybe at home, your lawn is growing back without any other measures. That means after 5 years cutting bamboo, the sprouts are coming out of the ground again and regrow. And it is actually the fastest growing plant known so far globally. That is also the fact why it is binding so much CO2. In order to grow in that speed, bamboo needs a lot of CO2 in order to be capable of its growth. But also, you see that bamboo is a very, very interesting material in the fact that it is not growing from inside out, as we usually know it from our trees here in the European context, but bamboo is growing from the outside in. So you see here a stem of bamboo in the first year of its growth, the second years of its growth, and the wall thickness is more or less increasing to the inside. The strongest parts of the bamboo are also on the outside, on the so-called skin or epidermis. You see it here, which is in complete contrast to usually what we know from the timber industry, where the hardest or the strongest part of a timber are found in the center. And I come back to the possibility of that bamboo. You know that in steel, in most of our steel constructions, we are also interested in the tensile capacity of the material. That means we are looking for a material which is very strong the moment I start to pull on it in two directions. That's also why we use why we use steel in the concrete construction, and why we reinforce usually our concrete constructions with steel elements. But what you see here right now is that usually steel has a capacity of, that is a number, 400 megapascal, which is classified usually as a material in the mid-range of the tensile capacity. But you see that some of the bamboo species, and I say some because we have worldwide right now approximately 1,200 species, and we're looking right now for the ones being most applicable for our research, that bamboo can reach, in the best case, tensile capacities which are double as high as those of construction steel. That, of course, is not the only fact, but given the fact that bamboo, and you saw it in those images, is a very porous material compared to steel, it also means that the strength compared to its weight, it is a big advantage in the factor almost of 5 compared to steel in terms of weight. So the bamboo, in the same amount of strength, is 5 times lighter than usually what we use with the construction steel. Plus, and that comes to it, what we call the specific strength. So when you put together the density and capacity, you come to a specific strength of so-called 560 MPa, which is compared to carbon, and you know that carbon became a new kind of superfiber as well, being used in the industry for airplane industries or in the car industries right now. We come close to these properties of a carbon fiber. So we are interested right now to combine this capacity of bamboo with a so-called modern building material like concrete. Concrete, as you saw, is the most used building materials right now worldwide, especially also in our so-called developing territories. And they were, of course, we're not starting this research just out of scratch. There were, of course, tests done starting in the 1950s, 1960s in the US, and recently also in Brazil, where the bamboo is growing, to now start to use bamboo as a reinforcement system, so putting it together as a reinforcement bar and putting that into concrete beams. These tests done by Professor Javami in 1995 in Brazil showed that a concrete beam, as you see it here right now, in a laboratory condition, that's very important, in a laboratory, or is able to cape 400%, so 4 times more forces than the same beam would have been able with a steel reinforcement bar inside. That is due because the tensile capacity of bamboo is much higher than the one of steel. But, and that's why I stressed the fact that this is a laboratory condition, and here you see different applications also for this bamboo. The laboratory condition is very important to understand because bamboo is a natural material. That means the moment you put this nice beam outside in the rain and into different climate, so-called micro cracks will happen and water will come into the beam and start to change the properties of the natural bamboo. That means the bamboo will start to decomposite. It will start to rot. The bacteria will start to eat on the bamboo and also debond the capacity between the concrete and the bamboo. So you see here in the end game that all of a sudden the bamboo is shrinking and leaves a void inside the concrete structure. And then the end of that one is basically, and there were tests also done, that failures happen. So that means all the tests being done here as examples in the 1950s and 60s in the US, the first couple of months these structures were behaving very, very well. But the moment these micro cracks and cracks happened in the concrete surface and the water reached the bamboo, all of these structures collapsed. And having known that, that was the reason why most of that research stopped in the 50s and 60s and was not considered anymore as a possibility to go further on and replace the steel with bamboo. But approximately 10 to 12 years ago, a new technology developed in China. And that technology is called the woven strand bamboo or woven strand board. And to make a long story short, is basically the Chinese found out that when you strip or when you make very, very thin fibers out of the bamboo, so not using the bamboo as a stem as we know it, as a ready-made piece coming directly out of the forest, that these ones, the woven strand boards, are split into small little bundles of fibers, then mixed with a resin or with let's say a glue, and then pressed together as a composite material consisting out of the bamboo fiber and an adhesive agent. So the production of this VSB or the woven strand board is of course due to the fact that the bamboo can be found in all of these areas. And our idea or our conceptual background of that is that all of a sudden the productivity or the chain of the productivity of a bamboo material like the woven strand board could be placed in the countries or in the territories and regions where the demand is given. And therefore, coming back to our yesterday's discussion about urban farming, for me, this would be urban farming. We do know that when we build cities and that we use materials from an agricultural background, that we could strengthen the rural-urban linkage or relationship. So the idea is that when you harvest this material, the bamboo as a raw material, you basically start, and you see it in the upper left image, you start to split it in even smaller pieces. You boil or carbonize it to get the sugar out of it, so it is not attractive anymore to bacteria, because bacteria and insects like the sugar usually in these organic materials. You dry it again, then you mix it together with the glue, and then in a so-called hot press, you press the material together. And the big advantage of that material being mixed with a glue or with an adhesive is that it is water resistant. So you see here the finished product. You maybe can recognize again the small bundles of fiber which are produced. It's a very, very dense material. It is compressed with a hot press. It is water resistant, so we do not have any problems anymore when the water comes to the micro cracks in the concrete. Plus, because the sugar is taken out of the material, that we make sure that bacteria and other insects are not interested anymore in eating it. We're doing right now in Singapore quite extensive tests, so we're trying to understand what is this process, so from a natural bamboo to a boiled bamboo and a so-called carbonized bamboo, and you see also the change of color, that a natural bamboo is still almost white because the sugar is still inside the fibers. The moment you start to carbonize the sugar or boil the sugar with heat, you know from cooking, the sugar gets dark or brown, and that's also why the difference in color appears as more you cook or carbonize the bamboo, as darker it gets. So right now, we're doing these tests. We're doing extensive tensile tests. So you see here the bamboo, the natural bamboo, in tensile machine that we're using together with our partner at NUS in Singapore, and trying to understand the charts of the tensile capacity. So you see here our test specimens. You see here how they are prepared for the machines. Again, you see here how we place them into the machines to make sure that we get the right results. We also, you see the funny shape that is necessary in kind of a bow, because you have to make sure that the machine is not destroying the fibers on the outside, which will change your test results. We do the same as with bending, so we're not only testing the tensile strength in the fiber direction, but also the bending capacity of the bamboo composite. And basically, you see here the failure then, so you pull on both ends as long as all of a sudden you get these fractal splits of the material. And right now we have graphs, or showing graphs, that basically our initial assumptions are correct, that with the process we can keep the strength of the material as we like. The same we do with compressive strength. So basically we put blocks into the machines and press on both ends. So we are also interested in understanding the compression capacity of these tests. You see again, they start to fracture. So we have shear failure in these elements. We don't have actually failures in any other. And we get very interesting results out of compression. You see here that the curve is going up. So that means compression is fine. And then we get to a point where certain fiber bundles fail, but the material recovers. So when you start to press again, the material has the capacity, because other fibers are taking over right now the action, that we have a very interesting curves showing that bamboo is such a flexible material, and you know it from also from these images from construction sites where it's used as a scaffolding, that bamboo is such a kind of living material that these ones would help us a lot in terms also of earthquake resistance in these composite materials. We do bending tests. So basically you see here that that is again a beam, a bamboo beam, and we press in the middle to it to understand what the bending capacities of that is. That's also an interesting fact that we realize in these tests that we don't have problems with cracking, so it only appears on the lower end, but because the material is so flexible that the upper part of the beam is still intact, and remember the graph, that you can take still capacity, load capacity, even so the material is not failing in an instant. Here you see the graphs of that again, so you have the first failure, again it picks up, similar to steel. So steel has the same capacity. In the first moment it starts to decrease the capacity and then picks up again, which is very important when you think about structures or concrete structures exposed to fire. So what we want to do is that our structures are not failing or collapsing in a second or in a moment, but that we have some time, even so the structures are deforming, giving still time for people to evacuate. And these results are very hopeful for us that the bamboo material has the same capacity. Right now, and that is a and that is quite a difficult task. We extensively travel to China. I mentioned that China developed this technology, and that is a very interesting thing because what we are doing right now is espionage. So we're going into companies in China and trying to find out how they do it, because we don't have this knowledge right now in our so-called developed world. We don't have the machines. We only can get these machines to produce the woven strand boards in China. And also we are right now proposing to our partners in Singapore to start the first, what we call Bambu laboratory, but we found out that's the wrong word. We have to use it now as a high tensile capacity fiber laboratory to install that in Singapore. And it is a very interesting fact because our partners in Singapore, remember when I said in the very beginning that these local materials are usually understood and connected to an outdated technology, to the past, to the unmodern terms. When you mention the word bamboo right now in Singapore, the people are not very much interested because they think that why should we even conceive doing research in bamboo? That's the past. So right now, with the help of Gerhard and others, we are trying very hard to convince our partners that looking at this material again could have actually quite a big kind of impact also for the building construction market in Singapore, because the dominant material there again is concrete. So we are in negotiations, and the moment I come back to Singapore, we have an important meeting. These are some of the machines which we would need to produce our specimens. And basically, right now what we're also doing is making first ideas of how reinforcement could be or could look like with this material being applied in the concrete mix. We filed for a patent. These are our partners that we're working together worldwide. I'm talking again about the local material with a global impact. It is research running right now only for half a year. And if you want to have more information on that one, please go to our homepage, and thank you very, very much.